we are reviewing variation parameters. This is a method of finding a particular solution to a non-homogeneous differential equation. So we're gonna just keep to second order differential equations at the moment. Today we're going to use t as the independent variable, not x. So we're going to start off with writing out our differential equation in the conventional form, say a standard form. Notice that that means that the coefficient for y double prime is 1. If it's not, you'll have to divide by whatever the leading coefficient is. So first, we suppose that we either know or we can find the solution to the homogeneous version of the problem. So we're going to find or know the solution, find or know the solution to the homogeneous version of the problem. And suppose that that solution be enveloped in a fundamental solution set. Once we have this, we then go back to our non-homogeneous, our original differential equation, and assume that our particular solution is a combination of the fundamental solution set, except instead of just not a standard linear combination of the fundamental solution set, but rather the things that multiply y1 and y2 are functions, some unknown functions of the independent variable. So that's the assumption for variation of parameters. And it turns out the formulas for what u and v are. So in fact, these are the formulas which will give you u and v. And I want to derive these, but if it's your life and if you don't care to see this derived, you can skip to the examples. Okay, now, so this is the outline of what we're going to be doing, right, for the method of variation of parameters in order to find a particular solution to a non-homogeneous equation. But I want you to notice something about this. Comparing it. Let's just quickly compare this to the method of undetermined coefficients. So for a method of undetermined coefficients, we had to have constant coefficients, right? So notice that for variation of parameters, the coefficients multiplying y and its derivatives do not have to be constant, but for a method of undetermined coefficients, they do. So in a sense, variation parameters are more general than method of undetermined coefficients. Also notice that for method of undetermined coefficients, the right-hand side function cannot be just anything, right? It's of a certain sort. It's some sort of polynomial, possibly times a simple exponential, times some combination. Okay, so it's limited in that sense. So variation parameters is more general. But in either case, either method, you need to know the fundamental solution set. All right, we'll go ahead and derive these formulas now. Okay, so suppose we in fact know the fundamental solution set. Now all these are functions of t, so I'm going to take a shortcut and not write t anymore. And we assume that a particular solution to the non-homogeneous differential equation is some combination of fundamental solution set where the coefficients are no longer constant, they're unknown functions. U and v are unknown functions of the independent variable. Now, to see what u and v have to be, of course, as always, when we make an assumption, we're going to have to find the derivatives here, and we're going to use product rule. So here's the product rule for the first term, and here's the product rule for the second term. Next, we're going to make another assumption. Now, the reason we can is because it works. Maybe that's a naive reason. So assumption 2 is that these two terms added together will add to 0, right? These two terms added together will be 0. Now, that's a simplifying assumption, and the reason is because we have to find the second derivative. And so if we differentiated, if we were to find the second derivative with these two terms in there, we would get u double prime and v double prime at some point. And we want to avoid derivatives of u and v that are higher than order 1, right? You just want u and u prime and v and v prime. Okay? And again, my naive justification implication for this is that it actually works out. Okay, so let's update y prime. So now we're going to differentiate again. So this is using the product rule on the first term, and this is using the product rule on the second term. Now, next is next we plug into. Next we're going to plug this into our non-homogeneous differential equation. So we have y double prime, and then p times y prime, and finally q times y. And that has to equal to the right-hand side function, g of t. We'll go ahead and distribute. We will regroup the terms according to the u terms, and also group all the terms that have a v in it. And then we'll group together all the remaining terms. There's just two of them. Here we can factor out the common factor, which is u, the unknown function. Over here, we're going to go factor out the common factor v. And now we're going to take advantage of the fact that y1 is a solution to the homogeneous version of this equation. That is to say, we know that y1 double prime plus py prime plus qy1 must be 0. Of course, that's relevant because that's exactly what we have over here. So this must be 0. And of course, the same argument can be made about y2. y2 is a solution of the homogeneous differential equation, so we know it satisfies it. So this means that this is 0. So we're left with all the remaining terms. So what we're going to do is now collect assumption 2 and this result we got after plugging in y prime, y double prime into the non-homogeneous differential equation. We're going to take those two equations. Notice we have a system, and we'll be talking about the system. Let's write the system as a matrix equation. Now remember that y1 and y2 are known, or we solve for them. And we don't know what u and v are, so u prime and v prime are unknowns. In the right-hand side column, we have 0 and g, which is the right-hand side function. So how do we know that there's a unique, there's definitely a solution for u prime and v prime in the system? Well, this matrix is invertible, right? Because it's the Vronsky. And we know the Vronsky is non-zero for our fundamental solution set. Well, we know it's invertible because that looks like a matrix you would find, take the determinant of in order to find the Vronskian. And we know the Vronskian is non-zero. And the Vronskian being non-zero, and that being just a determinant of this matrix, means that this matrix is invertible. So this is non-zero. Therefore, this matrix is invertible. And we'll just use the formula. So 1 over the determinant of that matrix. So just to remind you, formula for the determinant of a 2x2 matrix. 1 over the determinant, exchange the diagonal entries, and change the sign on the off diagonal entries. So 1 over the determinant of our matrix is going to be 1 over the Vronsky, because that's the definition of the Vronsky. We're going to exchange the diagonal entries and change the sign on the off diagonal entries. Therefore, we can just use the method of inverses here to solve for u prime and v prime. So multiplying the matrix with a column, we get negative y2 prime times g for the first component, and then y1 times g for the second component. So this means that u prime, now I'll go ahead and be more formal now, these are functions of t, is negative y2 times g divided by the Vronsky, function of t. And of course, if you want to find, to unprime the u, so to speak, we just anti-differentiate. So similarly, v prime is equal to y1 times g divided by the Vronsky. And then to find v, we just anti-differentiate. So that's how you get your formulas. So this is how we got our formulas. To summarize, we have a differential equation written in the standard form. We find a fundamental solution set. So that is to say the solution, this two independent solutions to this homogeneous version of the equation. We assume that a particular solution will be a function times y1 plus another function times y2. Our job is to find u and v. We used an assumption that u prime y1 plus v prime y2 is 0. Using those assumptions, we differentiate a couple times, plug that into our original non-homogeneous equation, and from there, and taking advantage of the fact that we have a fundamental solution. We know the solution to the homogeneous equation. We found that u prime y1 prime plus v prime y2 prime is g, which is the right-hand side function. And then we solved the system for u prime and v prime, and then anti-differentiated in order to find u and v. And then our particular solution once we find this, of course. Let's do some examples. So here's a second order differential equation. It's non-homogeneous. We don't have constant coefficients. So let's see if we can find a solution to the homogeneous version of this. You might recognize this as an Euler differential equation. So we know that we can find solutions in the form of the independent variable t here raised to some power r. Or of course, if you already know the characteristic polynomial for Euler equation, you can also use that to find what r is. Plug this in, t squared times y double prime, negative 3t times y prime, and 4 times y. We're assuming t is positive, so this cannot be 0. So this polynomial must be. So our characteristic polynomial has a repeated root multiplicity too. So you need to recall from the section on Euler's differential equation that fundamental solution set would be t to the r, where r is 2. And here we would have t to the r, but we have to make sure it's y2 is independent from y1, so we multiply by natural log of t. So we found fundamental solution set. So of course now we're looking for the particular solution. So we're going to assume that the particular solution is some combination of the fundamental solution set, where the coefficients are not constants, but rather functions. U and v are functions of the independent variable t. And we found that we had a further assumption. So I'm just going to go ahead and use the formulas to get u and v. Well, let's first, apparently we need the Wronskian, so let's compute that first. That's the determinant of y of the matrix. We have y1 and y1 prime, y2 and y2 prime. Two of the terms add to 0, so we're left with t cubed, which is not 0 because t is positive. All right, so let's find u. So u is negative y2. U is the antiderivative of negative y2 times g, which is the right-hand side of our non-homogeneous equation, divided by the Wronskian, which we computed to be t cubed. So this looks like an integration by parts. So according to integration by parts, this should be negative 6 u times, well, so that's u of t. Let's keep that in our back pocket. We also need to find v, the antiderivative of y1. Y1 is t squared, times g, which is the right-hand side, divided by the Wronskian, t cubed. Okay, so that's our antiderivative up to a constant. All right, so now we can write down the particular solution, which is u times y1 plus v times y2. We'll go ahead and simplify this. Apparently, that's a good particular solution. I think I made a small mistake. This is u is negative 2t cubed right there. So this would become 5 So we do have a cancellation. So it looks like our particular solution is just 2/3 of t to the power 5. So now we can get the general solution. It is a combination of the fundamental solution set plus our particular solution. So this is our general solution to the non-homogeneous equation. Here's another example. We first find the fundamental solution set. And we have constant coefficients, so we can just write down the characteristic polynomial. We see the roots are real and distinct. So our fundamental solution set is e to the 3t and then e to the negative 2t. To find a particular solution using variation of parameters, we assume the form that our particular solution will take. We also assume that this is 0, and sticking our assumptive form
find u of t
into the original non-homogeneous equation.
using the formula
y2.
y2.
That we use method of inverse here to find the solution for u prime v prime
times g.
system, then anti-differentiate. And we found that u is the
That's of course the right-hand side of our differential equation, divided by the Wronskian.
I guess I need to compute the Wronskian. So 1 second. So that's y1 and y1 prime. The next column is y2 and y2 prime. Computing the determinant, we find that it's not 0, right? Let's go ahead and do our computation here.
And use integration by parts. So similarly, we're going to solve for v, y1, g, divided by the Wronskian. Simplify, use integration by parts. Now that we found u and v, we can write down our particular solution. It is u times y1, which is e to the 3t, plus v times y2. We see the exponentials simplify. We get e to the 0. And then combining the t terms, we get negative t. Combining the constants, we get 1/6. So now our general solution is a combination of the fundamental solution set plus the particular solution.